Okay, what that means is an update on where's the focus.
Well, I guess we should start. We have 4 panelists, and Jim Overland, Amy Solomon, Tom Haine, and Fiammetta Straneo. And I think they'd rather sit down there so they can see the talks. But I think what we'll do is, if they can limit their talks to about 25 minutes, that'll give us about 12 to 15 minutes to have a kind of a group question and answer at the end of the session. So we'll hold questions until all 4 have spoken, and then hopefully questions will be answered by other speakers. So our first speaker is Jim Overland, and he's going to talk about the immediacy of Arctic change, new 2016-17 extremes.
Well, good morning, everybody. A lot of the material from this talk comes on what can be considered the 3rd Arctic Climate Impact Assessment run by AMAP. They're now called SWIPA reports. The detail what's in there, but then SWIPA becomes another unknown acronym. But I can report that the full report is now out and available as of several weeks ago. So a lot of your colleagues have contributed to that report. This slide is really symbolic of the point I want to get across here. There's 2 main issues here. Permafrost as a combination of soil and ice has been around for 100,000 years, and when the water melts and runs out of it, that's an irreversible change. You can't put the water back into the soil after it runs out. So there are a large number of these types of irreversible changes going on right now in the Arctic. The second point, you see a large amount of ice-free open water. So with more open water, you can have higher waves and you have more erosion. So there are positive feedbacks within the Arctic system that are tending to accelerate the changes going on, and that's happening right now as well. So the issue for the Arctic is what's happening now in the next 20 years rather than concentrating on 2100, something like that. If you step back and look at the big picture from the climate models and what they say about air temperatures in the future, these curves are from 1900 to 2100, and 2 scenarios. The blue scenario is 4.5, and it's an ambitious but not unreasonable mitigation scenario, and the red is the business as usual scenario. In fact, that's the one that we're actually on. And the bottom line point here is, under the Paris Accords, they want to limit global temperatures to below 2 degrees, and that could happen with an ambitious mitigation scenario as shown on the right, but the center shows the annual mean temperatures from the Arctic, and just like the observations, the future change for the Arctic is double what it is for the global mean. And if you look at the winter months, we're going even further. So even if we hold, so key point I think to tell your colleagues is even if we hold to a 2 degree limit for the globe, the Arctic's going to be a completely different place than it used to be. As you know, the ice has been retreating. On the right is the September ice extent. In 2007, that first downward bump, we thought there might be a tipping point, that once we were so low, we would open up and absorb more heat and open water, but we regressed back towards the mean. And most experiments now look that the ice is really driven by temperature increases, and which is driven by the CO2 increases. So if you slowed or stopped the temperature increase, you would also stabilize the ice extent. And we don't tend to see any runaway tipping point for sea ice. One scary point that came out of the SWIPA report was related to permafrost area. Up till now, we've affected about 5% of the permafrost area, but in the next 20 years, we'll be influencing 20 to 30% of the permafrost area. So in terms of impacts on infrastructure and so forth, we've just started to see major impacts on that. The other wild card has to do with melting of glaciers and ice sheets. This compares the two scenarios, the higher emissions in red and orange and the lower one in the purples. But the takeaway here is that the difference in timing later in the century versus earlier in the century, you have a much higher ice loss in the second half of the century. And what's going on here is as you warm the Arctic, you also warm at a higher altitude. And in the second half, the annual zero temperature reaches the level where most of the ice sheets sit. So you're melting the lower part of the glaciers now, but it'll hit the max, the altitude where most of the ice sheet sits early in the second half of the century. So big impact in the second half of the century on sea ice. So don't think linearly in terms of potential ice sheet impact on sea level. The other point I want to get is we're really uncertain how fast we're changing and where we're going. We know the sign of the direction, but the magnitudes coming out of the models seem really slow compared to observations. And we've seen, I think we keep seeing surprises that we didn't expect. The low sea ice in 2007 was one, but we've seen a couple of others in the last couple years, and I call this the big melt where we're already outside the envelope of previous experience. So there's some problems with the models, and we can't strongly extrapolate from where we've been because we're already outside the envelope of any sort of Gaussian behavior. So one of these was temperatures in winter 2016 and on to fall there. We had 6-degree temperature anomalies over most of the Central Arctic in winter and spring of 2016. This number of 6 degrees is almost double what the previous anomaly was. So we're not going up incrementally. We went up almost double in one particular year. And looking for the cause of that, the tropospheric jet stream is shown on the right here, and the winds follow the contours. And you see the normal polar vortex, which is one, is split into 2 pieces. And if you follow the purple line, we're bringing subarctic warm air and moisture in across Alaska and then around from the Atlantic into the Arctic, and that penetrated all the way to the pole. You may have read back then in January 2016 about melting temperatures at the North Pole. That extreme temperature from winter and spring 2016 was seen again in the fall. One of the things we don't know is how do we get this year-to-year persistence in a real chaotic atmosphere. But after this, we went back to more the high but not extreme temperatures here in 2017. And the other big thing is you really consider a change of phase on sea ice, where we went from mostly multi-year sea ice to mostly first-year sea ice. And I like this one. It turns out that the satellites can see salinity, and old thick ice has lower salinity than first year new ice. So the old thick ice can be mapped out, and it's shown here in red for especially the early years here, and then it transitions to mostly blue colors starting in 2007. And so essentially we've lost 60% of the old multi-year ice. And the biomass people that keep track of volume are saying we've lost 75% of the volume of sea ice in the Arctic. Just incredible difference. I flew on the NOAA plane 2 years ago, and it was all flat first year ice compared to 20 years ago when we were walking around with pressure ridges and drilling holes. So absolute difference. And so the ice is thin and more mobile. In the old days when it was thick and solid, it was really a flywheel for global climate. Nothing really changed it much. Where now the Arctic is becoming much more coupled with the global climate system. Another essential surprise and outside the envelope was related to those low, warmer temperatures. Rather than just thinking about sea ice loss in the summer, most of winter through spring of 2017, the ice extent was lower than ever observed. So you were seeing big effects in the winter as well as the summer. And this goes against the normal thinking. Well, thin ice grows faster, and so if you had thinner ice at the end of the summer, you could recover very quickly. Well, that paradigm is no longer working. Another scary thing that when we were working on the SWIPA sea ice review the last 2 summers is, even though the midsummer 17 didn't really have a record sea ice loss in extent, when we looked at the satellite picture, and this covers most of the central Arctic, the sea ice concentration is low. You sort of see all these dark holes in there, and when you have open water, that's areas for absorbing sunlight, and the flows melt from the side on that. So in terms of how soon are we going to have an ice-free summer, this picture really makes me scared from the point of view that we're very close to the radiative equilibrium where we can go to an ice-free summer, and this picture from 2006 and something similar 2007, 16 and 17 showed the Swiss cheese sort of look for the ice. So I'm not a believer in the models that say ice-free Arctic by 2060. I think we're looking at it before 2030 based on looking at real observations. And we were involved with evaluating some of the climate models for sea ice loss. And here's what all the models show. If you average them all together, you get the blue and yellow lines. The black line is the data. And so, the models all lose sea ice. And so we can go with that. But what really, after staring at this for a week, what really got you is, even back on Haine casting, the large differences between the models and whether you can have any real credibility from this. This is from our 2013 paper. It turns out that the difference here, especially on the Haine cast, is not that the sea ice models are bad, but they haven't really figured out the clouds, especially Arctic clouds. And so the differences in clouds are causing differences in the radiation budget, and the Arctic sea ice is trying to do its best to answer the problem you proposed to it, and the sea ice is changing, trying to adjust to different cloud amounts, high versus low, in the models. So it's more, the wide range is more due to radiation and cloud forcing of the models rather than the sea ice. So as I said, we have a lot of indication, but I think where we really are is that we certainly know the direction, but we don't have a real firm handle on the time scale and the rate, other than it's really large, and we keep seeing surprises that are larger than we think. So I want to end up with some latest news here. Another surprise, the sea ice right now in the Chukchi Sea is at the lowest that's ever been observed. You can see the ice map on the right, and the time series is on the left. Another major change. It looks like the Alaska side for the last few years is retreating more than other parts of the Arctic. And part of what I'm interested in is can changes in the Arctic influence the jet stream and change the weather down here. And so at the same time this was going on, they had snow here in New Orleans, and they closed the airports in Atlanta and Newark, and we have major fires in California. And so at the same time we lost the ice there, we had this very wavy jet stream. So the way to read this is the winds follow the contours there, and so the contours all head up the west coast well into Alaska, and then they curve over, and then the winds are out of the north, bringing the cold air down all the way, aimed down here to Louisiana over the weekend. And the connection here is the air temperatures over that ice-free area, are -1, where normally it would have been like -20, and warm air is less dense, and it increases the difference between pressure surfaces. Essentially, it pushes the pressure surfaces higher that helps lock in this wavy pattern. So there's what we've been saying is the Arctic doesn't cause changes in mid-latitude weather, but once this wavy pattern gets set up, the Arctic here in Alaska can help, since the forcing is in one location, it helps lock into the location. So we think the ice loss north of Alaska and west of Greenland are the two regions that can affect the duration of cold events on the east coast of the U.S. and the fire situation in California. So my final message is Arctic change is happening now. Impacts are strong and will continue for the next 20 years. We should really be focusing on how to improve the models so we can get a better handle on the timing here. But the take-home message is in the last couple of years we've seen observations well outside previous experience, and we will tend to see that to continue. So thank you very much.
Okay, again, I think nice if we could save our questions and have them all together at the end. Our next speaker is Amy Solomon, and she's going to talk about formation of a Click-Clivar Northern Regions Regional Panel to advance the understanding of the role of the Arctic in global climate. Oops, sorry.
So thank you to the organizers for giving me the opportunity to introduce this new regional panel, which is jointly sponsored by the WCRP Cryosphere Program and the Role of the Ocean in Climate Program. And the focus of this new panel is on the role of the Arctic in the global climate system. So the focus of this panel is going to be on spearheading international initiatives to look at the climate variability in the new Arctic. And so this is an animation, this is a 7-day forecast initialized on November 29th. So just to orient you, this is Alaska, and this is Russia. And the black line here is showing the area of free ice. And as Jim just said, this year, the Chukchi Sea is essentially ice-free, and that's never been observed before. And these other figures are showing at upper right sea surface temperature, and the lower figure is wind speed, and the left is showing the heat flux of the ice to the ocean. And so the question is, what caused this very warm water that keeps the Chukchi Sea open? Is it because of this longer open water season and the accumulation of heat? Is it because of additional transport from the North Pacific? Is it because of change in synoptic atmospheric patterns? Or is it because of the multi-year ice regime transitioning to a first-year ice regime? And what we are looking into is the coupled nature of this phenomena, that all of these differences, all of these changes are important. The changes in the ocean, the changes in the atmosphere, and the changes in the ice. And I also want to point out here in the region of the ice-free, in the Chukchi, the wind speeds are greater than 16 meters per second. So naively, you would think that if we have longer regions of open water, that would be a positive thing for stakeholders like shipping and fishing. But what this shows is that's really not true. If you look on the right, this is a weather report for Barrow, Alaska. And what it shows is there was a high surf advisory at Barrow on November 10th. And this has never been observed before. So at this time, there were whitecaps observed. And in the upper figure, this is some text from a wildlife biologist in Barrow talking about the complications for the whaling industry. And what this is highlighting is that we don't know what the impact of this new Arctic is going to be on stakeholders. So this is the CLIVAR organizational chart. It shows the core panels on the left and the research foci on the right. And so we've already established very close collaborations with the Southern Ocean Panel. We're going to have a joint meeting in Polar 2018 in Davos in June. And we have so we've only been in existence for a few months, but we already have relationships with the Pacific Panel, where we're both interested in the impact of ENSO on the Arctic and the impact of changes in the North Pacific climate on Arctic, and the Atlantic Panel, where we're interested in how changes in Arctic freshwater and heat fluxes are affecting AMOC. And with the Climate Dynamics Panel, where we're interested in how changes in storm tracks, for example, blocking over in the North Atlantic, how that affects the mass loss of the Greenland Ice Sheet, and how the Arctic, as Jim was talking about, affects storm tracks. And there's also very interesting collaborations that we would like to set up with the Ocean Model Development Panel and the Global Synthesis and Observations Panel. And so this is just showing that this new panel, the Northern Oceans Region Panel, is filling a really important gap in the whole CLIVAR structure. So similarly, this is the CLIC organizational chart, just to show that we're filling this very important gap is in the CLIC structure as well by representing Arctic sea ice processes and climate. So this panel is an international panel to coordinate and facilitate activities on the role of the Arctic Ocean in the context of the global climate system, and that's from a coupled ocean-air-ice perspective. And I think we've organized this panel in a very unique way. We've already established 6 specific task teams, and we've chosen our panel members based on their expertise in these areas and the fact that they are actively working on research in this area. So we're not only able to spearhead these international initiatives, we also, by interactions within the panel, are informing our own research activities as well. And so these task teams are development of a state-of-the-art Arctic Ocean reanalysis, the role of the Arctic Ocean in Arctic amplification, advancing the understanding of climate variability due to Arctic mid-latitude linkages, quantifying the response to natural external forcing and internal variability in the Arctic Ocean, promoting studies to assess model errors in Arctic projections through initialized forecasts, and Greenland Ice Sheet ocean interactions. So we have 14 members, and they're represented a number of different European nations, as well as all over Scandinavia, the US, Canada, and Asia. So Task Team 1 is the development of a state-of-the-art Arctic Ocean reanalysis, and this is to address the critical need for adequate Arctic, subarctic ocean reanalyses that are needed for forecast model initial conditions and for validating the climate models. And we need to improve our representation of these key water masses in the reanalyses. And this is a really excellent opportunity for collaboration across CLIVAR, from their regional panels to their observational panels and also their modeling panels. So we recently had a teleconference focusing on this first task team. And this teleconference, we discussed a paper that just came out that compared 10 different polar ocean reanalyses, or AURAs. And these are the 10 different models that were compared. And they all use completely different ocean data simulations, sea ice data simulations. They all use completely different atmospheric forcing. Some are coupled, some use era interim, and they all use very different resolution. But the focus is on looking at diagnostics in both the ocean and the sea ice. So there are diagnostics that they have developed to look at changes in heat, salinity, and freshwater content, transports and currents, and mixed layer depth, as well as sea ice concentration, area, volume, and snow depth. So they've developed these diagnostics to be able to assess the differences across these ocean reanalyses. And these two figures really illustrate the results of that study. The left is showing the Arctic snow volume. It's the monthly climatology from 1993 to 2010. And the colored lines are showing the different models. The black line is showing the ensemble mean, and the bars are showing the spread across the different models. And the black dashed line is the Warren climatology. And what this is showing is that the data used to assimilate, that is assimilated into these different models, is not sufficient to constrain their estimates of the monthly climatology of the snow volume. So this is an indication that there are differences or model biases that we need to address to get a better estimate of snow volume in the reanalyses. Another important issue is that the Warren climatology has very little data in it, and we need to be able to compile all of the data that we have from the different Russian drifting stations. There's a lot of data out there. We need to have an effort to bring all that data together to be able to simulate it and to evaluate these models. And so this is a really, really important variable. Snow is very important for many reasons, one of which is that it changes the albedo. It also has a very important impact on the flux of heat through the ice. So this is a variable we need to understand better in order to first determine whether the models are adequately simulating it, but also to assess model biases. On the right is a similar picture. This is the spring to fall ice volume loss. It's averaged from 2000 to 2012. It is averaged over the IceSat domain, and the left is showing the observations, and the blue is showing the 10 different models, and the orange is showing the multi-model ensemble mean, and the black bar is showing the spread across the models. And this is showing a similar picture, that the models have a huge spread, meaning that the model physics is so different across the different reanalyses that we cannot constrain this variable. This is a very important field. We need to have a better understanding of the ice loss from spring to fall to be able to evaluate the climate models. So task team 2 is the role of the Arctic Ocean in Arctic amplification. And this task team will address the questions: do we have adequate measurements to evaluate the role of the Arctic, subarctic ocean in Arctic amplification? What measurements are needed to evaluate this variability in climate models? What metrics are needed to assess these mechanisms in climate models? And how to quantify internal variability in Arctic amplification? And so I just want to stress here, there's a lot of overlap between these task teams. And so you'll see that internal variability comes up in a number of these different task teams. And it's very important given that the climate record is so short in the Arctic. So there are a number of different mechanisms that have been proposed for Arctic amplification, from the seasonal redistribution of heat, that you get heat into the ocean in the summer that comes out in the winter, to changes in surface stratification, to changes in the cloud cover, to changes in heat and moisture fluxes coming in from the lower latitudes. And the Arctic amplification in each model is the net result of all of these. So the way in which the models represent all these different mechanisms determines what the Arctic amplification will be in the model. And all of the models do this differently. And one really interesting mechanism is called Atlantification. And this is from Polyakov et al. 2017. Right now, the water that comes in from the Atlantic is very deep, and there's a halocline that prevents it from being mixed into the mixed layer and impacting the sea ice. But what this hypothesis says is that in this first-year regime with more broken up ice, we're getting more wintertime convection, which will be mixing up this very deep water, eroding the halocline and playing an important role in the melting of the sea ice. And it's really important to determine whether the climate models are adequately simulating this process, given how diffusive these climate models tend to be. So what's really important is we need more observations, because as I said, there are all these different mechanisms that are important for the amplification, and each climate model does this differently. And there's a campaign coming up in the spring of 2019, it's called Mosaic. And it's going to be a drift experiment where the icebreaker will be in the ice for a whole annual cycle. And with this drift experiment, they'll be taking very intensive measurements in the ocean, even up right against the ice, which is the information that we need, throughout the ice, all the different variables within the sea ice and the snow, as I said, and also with the atmosphere in the clouds, there's going to be a tethered balloon, there's going to be a number of different aircraft campaigns, and there's also going to be intensive measurements of aerosols, which we have essentially no measurements of in the Central Arctic. So hopefully the data set that we will compile from Mosaic, we can see if the relative magnitude of these different mechanisms in the ocean and the ice and the atmosphere and the clouds is being represented adequately in the climate models. So the third task team is advancing the understanding of climate variability due to Arctic mid-latitude linkages. And right now there already exists a US CLIVAR Arctic mid-latitude working group, but it's ending at the end of next year. And this group has been really, really effective at building a community and identifying the issues. And they have even proposed pacemaker experiments that we hope to be able to bring to the international community. So this is a slide to illustrate some of the findings from this working group. If you look at the upper right, this is showing the upper figure that the long-term warming trend from 1960 to 2010 is a uniform warming. But if you look at the same average from 1990 to 2010, you see there's a cooling over North America and a cooling over the Eurasian continent. And the hypothesis for this, as Jim was explaining in the lower left, is that due to climate change, and a reduction in the temperature gradient from equator to pole, you would have a wavier, slower jet stream. This is just one of the many hypotheses. But you see this pattern in the lower left. This would enhance advection of cold air from the Arctic over North America and over the Eurasian continent. But the figure on the right, the lower right, is showing this is a model experiment where from McCusker et al. 2016, where they did a very large ensemble to look at the relationship between changes in sea ice and changes in the mid-latitude climate. And what they found in this is that there was only one of, I think they did 600 different simulations, only one of those simulations, they had cooling over North America and the Eurasian continent that looked like the pattern that we're observing, and it was not related to sea ice. So and there are other studies that have the opposite result. So the pacemaker experiments that are proposed by the working group are really important for really nailing down these relationships and quantifying them relative to natural variability. So the fourth task team is quantifying the response to natural external forcing and internal variability in the Arctic Ocean. And as I said, these task teams, they're not exclusive. So this task team is very important for, I think, almost all of the task teams I've already mentioned. And this is from a paper by Fife et al. 2017. It's showing the 15, 20, 25, and 30-year trends zonally averaged in the Arctic. And so this is from 1,000 to 300 hectopascal. And it's the upper figure is showing the era interim, the reanalyses. And the second figure is from a large ensemble composed of CESM1 and CAN-ESM2 simulations, so 90 members. And the second line is for the external forcing, so the mean. The third line is showing the contribution of internal variability to these very long trends. And the lower figure shows the sum of the internal and external variability. And so there's a close correspondence between what the model is producing in the sum and the reanalysis on the top. And so this is just to highlight that even on these very long timescales, essentially the timescales of our observations, internal variability can be dominant. Another focus will be quantifying the role of the natural forced variability. So this is the Arctic sea ice response to the tropical volcanic eruptions. And so this is from Gagne et al. 2017. It goes from 1960 to 2005. The green line is showing the sea ice extent anomaly response to the external forcing. And if you just focus on the two largest volcanic eruptions in the 80s and 90s, the blue lines are showing the aerosol optical depth. The light blue is for the tropics, and the dark blue is for the Arctic. And you can see the very large response in sea ice to these tropical volcanic eruptions. And also, when the eruptions are close in time, since the impact, the response is about 2 to 5 years in the Arctic, they can be additive. And so we need to be able to quantify this in order to understand the observational record. So Task Team 5 is to take the lead on promoting the studies to assess model errors through initialized forecast. And this is the opportunity to contribute to a number of different WCRP grand challenges. There are three main ones. The first is to provide regional climate information. The second is near-term climate predictions, and also this very interesting grand challenge on melting ice and global consequences. So the focus of this task team will be spearheading efforts to improve initialized forecasts. And the hypothesis for this task team is that many biases in the climate simulations are due to fast processes such as clouds. And this can be diagnosed more effectively in short forecasts. And so if you look on the right here, this is the Arctic sea ice extent from NSIDC. It's over the annual cycle. The green dashed line is 2012, which was our record minimum. And the red is showing 2017. And so in July and August, it looked like we were tracking the 2012. And it was predicted that we would have a record minimum this year, but that didn't happen because the rate of the sea ice loss started to decrease in September. And actually, as Jim mentioned, right now, the sea ice is the lowest it's ever been observed at this time. So on the left is the short-term forecast to try to predict this variability. And so there are two sets of forecasts. The first ensemble is an ensemble initialized on August 10th. So that's the time when we were tracking 2012. And the spread is from perturbations in the sea ice thickness. And the second ensemble was initialized on August 27th. And it's an ensemble using the same initial sea ice concentration and thickness, but it's perturbed by using different GFS forecasts as lateral boundaries. So these are two ensembles. One is due to perturbations in the sea ice, and the other is due to perturbations in the atmospheric forcing. And so you can see in the first ensemble, the X's are AMSR2 estimates of the sea ice concentrations averaged in the Beaufort-Chukchi seas. And you can see with the first ensemble, with the perturbations, we can do a nice job of simulating the melt back between August 10th and August 26th. And if we use those initial conditions for our ensemble from August 26th to September 12th, you can see that we're completely missing the observed sea ice concentration of September 12th. So we're not able to simulate the beginning of the freeze up. And this is an indication that the model physics, there's biases in the model physics that we can diagnose more effectively with this type of forecast. So the sixth task team is the Greenland Ice Sheet Ocean Interactions. And I only want to say a little bit about this because Fiammetta will be talking about this in a few minutes. But this shows the mass balance of the cryosphere divided into the West Antarctica, East Antarctica, Antarctic Peninsula, and Greenland. And this is from the early 90s to 2014. And this is just to highlight that the majority of the mass loss is happening over the Greenland ice sheet. So I'm not going to talk about the processes, around the Greenland ice sheet that will be the focus of the talk in a few minutes. I just want to stress that this is really highlighting the interactions between the lower latitudes and the Arctic, because the subpolar water is anomalously warm, and there are many different mechanisms that are causing that, from atmospheric forcing to changes in the heat flux absorbed in the ocean. We have to look at this from a coupled perspective, because it's the changes in the subtropical oceans which are affecting the Arctic, which are playing such an important role in the melting of the Greenland ice sheet, which will be described in a talk in a few minutes. So thank you for your attention. Was it?
You surprised me, that was quick.
Should we go on?
Should we go on?
It's up to you.
Oh, you've got more, okay. I guess we were gonna save the questions until then, and you've given us lots of catch-up time. So let's go ahead and do that and have Tom Haine talk. Tom, are you a Mac or a, okay.
Two. Stations are 0, 9.
Okay, let's see. So I'll close this one. Why do you want it here? What's the scoop? I'm sorry, do you see it? Under presentations, it seems like it should be there on the Mac.
Yeah.
Oh, here we go.
The first one.
This is the one you want?
Yeah.
Okay. So now we're going to have Tom Haine. He's going to talk about status and impacts of Arctic freshwater export. Thank you.
So let me just play that.
That should work.
Okay, thank you very much for this opportunity to tell you about the freshwater changes in the Arctic and their potential downstream impacts on the North Atlantic Ocean. So this is going to be a basin scale into annual perspective. So I'm going to be talking about the freshwater system integrated over the whole of the Arctic, and then look at the downstream impacts in the subpolar gyre of the North Atlantic. And it's going to be an interannual perspective. I'm going to be taking decadal averages. That has some advantages because, for example, it allows us to compare to climate models, which might arguably get basin scale interannual mechanisms more or less right. But of course, it has disadvantages too, because it's disconnected from the actual observations of, for example, the Arctic sea ice change or in situ changes in the Arctic Ocean. Most of what I'm going to be talking about is from these papers, and in particular, the second bullet, this paper in Global Planetary Change. And I'll mention some of my co-authors here. There's many of them. I didn't have opportunities to list them all on the title of the presentation. I'll touch a little on the work with Carl Stewart, and then some speculations about what's happening in the Atlantic, and try and roll that into a discussion of recent work on subpolar North Atlantic variability. Okay, so the first thing I want to do is construct a freshwater budget for the Arctic as a whole. And I'm going to compare the decades of the 1980s and the 1990s to nominally the decades of the 2000s. And on the left-hand side, you can see the Arctic Ocean, and you can see the control volume that I'm going to use. So if you can see those red lines, you've got one at Bering Strait, Davis Strait, Fram Strait, BSO is the Barents Sea opening. So the budget I'm going to construct is within that control volume. And then on the right-hand side, you can see the schematic that I'm going to use to talk about the various different reservoirs within that control volume of fresh water, and then the various different fluxes. So in the center, you can see the reservoirs of liquid fresh water, which is the large dark blue rectangle, and then multi-year ice and seasonal ice. And the scales of those rectangles, it reflects the size of those reservoirs. And so on the top right, you can see a 4,000 kilometer cubed scale. On the left-hand side of the schematic diagram, you can see sources of fresh water to the Arctic Ocean. So they are P minus E, precipitation minus evaporation, runoff, and flow through the Bering Strait. And then on the right-hand side, you see the outflows, which are to the Atlantic through Fram Strait, which is split more or less evenly between ice and fresh water, and through Davis Strait, which is almost entirely liquid fresh water. And the size of those yellow and green boxes reflects the size of those fluxes, and so that would be 4,000 cubic kilometers per year for each of those fluxes. So my path through this talk is I'm going to say a little about sea ice, I'm going to talk a little about liquid fresh water, how that's been changing, then I'm going to talk about the fluxes, first the inflows and the outflows, we have observations of those. To construct a budget, that's going to be the fourth point. I'll say a little about mechanisms that control the variability in this system. Prospects I'll touch on briefly, and then the final part is going to be on impacts in the subpolar North Atlantic and trying to marry what we see in the Arctic with what we see changing in the subpolar North Atlantic as well. Okay, so let's start with Arctic sea ice volume. Jim set the stage very nicely to this. For our purposes, this is the most useful time series. It's from biomass, so that it's an assimilation system, and it's a time series of the freshwater volume. So this is the equivalent amount of liquid freshwater stored in sea ice from this biomass data source. You can see the seasonal cycle, but then you can see the long-term decline in sea ice volume starting circa 1980 or 1985. Now, of course, the sea ice volume is declining for two separate reasons. One is the sea ice extent is declining, but second, the thickness of the ice is declining as well. And the number that Jim quoted of 75% loss, I think corresponds to the last few years in summer only having 25% of the freshwater volume that they did, for example, in the 1980s. If you look at the decadal averages, you can see the 1980 to the 2000 mean and the 2000s mean. Then you've lost about 3,500 cubic kilometers in the decade of the 2000s relative to the decade of the 80s and the 90s, from a nominal starting level of about 17,000 cubic kilometers, which is our Argard and Carmack's estimate before anthropogenic effects took hold. Okay, so we've lost 3,500 cubic kilometers of sea ice over that time period. Now let's talk about liquid freshwater. So we quantify liquid freshwater as a salinity anomaly. So the equation on the left shows how that works. So the salinity is S, it's a function of depth, it's also a function of space, latitude and longitude and time. And we integrate the anomaly of that salinity from a reference salinity, which is SREF 34.8 in what I'm showing, and we integrate that in the vertical. So this M thing is the thickness of fresh water that you would add to a column of seawater with a salinity SREF to achieve the observed deficit in salinity. In other words, you've diluted the surface of the Arctic Ocean with this thickness of fresh water to reach the observed fresh state. And that has changed over time. So you can see in the top right, there's some papers cited here which show the extra liquid fresh water integrated over various different regions in the Arctic. For example, the one I like best is the final one, which is the 1990s to 2012, Rabes al 2014. It says there's an extra 12,000 cubic kilometers of liquid fresh water integrated over the whole Arctic. And I think Benjamin Rabe's paper from 2011 with the two figures below shows that very clearly. So now you have maps of the liquid freshwater content. It's measured in meters, so it goes from 0 meters to 25 meters. Most of the liquid freshwater in the Arctic is stored in the Beaufort Sea or the Beaufort Gyre in the western Arctic, less so on the Atlantic side. And if you look from the 1990s to the mid-2000s, you can see it's increased. So in the Beaufort Gyre, for example, it's gone from maybe low 20s to high 20s of meters of fresh water. So 12,000 cubic kilometers extra in the Arctic Ocean, significantly more than the loss of sea ice, which is 3,500 cubic kilometers. And concomitant with all of that is that it's getting fresher, and Jamie's paper from 2012 shows that as well. It's significantly fresher by oceanographic standards. So now let's look at the fluxes. We'll look at the inflow fluxes first and then the outflow. So this diagram shows time series of our best estimates for the inflow. At the top you can see P minus E and then runoff. So let's talk about P minus E first. There is no good data source for precipitation or evaporation over the Arctic Ocean. So this has come from an atmospheric reanalysis, the ERA interim reanalysis. And although you get a very nice time series with lots of data, it's somewhat deceiving because we really don't have a good handle on what the errors are in this product. Over on the right-hand side, you can see the little red bar. That is the standard error in the decadal average for the 2000s. But I think it really underestimates the true error in this product. We don't know what the P minus E over the Arctic is. Nevertheless, if you all of that put to one side, you would find that P minus E is increased slightly for the decade of the 2000s compared to the previous couple of decades. Runoff is a somewhat similar situation. We have an estimate from ERA interim, which is comprehensive but uncertain, and there are some observations from discharge, from river gauges. The problem with those are that they're incomplete, and so you have to extrapolate a large amount, maybe a factor of 50% or more, to estimate the total draining into the Arctic Ocean. The runoff is the single largest source of fresh water in the ocean, about 4,000 cubic kilometers per year. So that's equivalent to the total loss of sea ice over the decade of the 2000s. Okay, and then beneath that you can see Bering Strait. So Bering Strait inflow has been measured by the Applied Physics Lab at University of Washington, in particular by Rebecca Woodgate, for many years now. And that continues. And it is probably the oceanographic strait where we have best measurements. And you can see that over the decade of the 2000s, there's been a slight increase in the freshwater source. It's it's about 2,500 cubic kilometers per year. There's a rather small standard error on that estimate. And that is increased for the decadal average over the previous best estimate for the 80s and 90s as well. So the take-home message from this slide is all of these sources are increasing, although there are large errors associated, in particular with P minus E and runoff. What about outflow? So at Fram Strait, you have to measure two things at once. You have to measure the liquid outflow. You do that with oceanographic moorings. You have to measure the solid outflow as ice. You can do that with satellites. And they're about the same in terms of their relative importance. So the sea ice is at about 2,000 cubic kilometers per year. That has declined slightly for the decade of the 2000s compared to the previous decade. You can't really see the change on the diagram here. And there has been a corresponding slight increase in the liquid outflow. So to get taken together, they're about the same, but there's been a shift from ice to liquid freshwater. And at Davis Strait, there is a relatively short time series. It started in the mid-2000s. This is Craig Lee and Beth Curry from the University of Washington. And although there's a lot of interannual variability, as you can see, there isn't really very much change in the Davis Strait measurements. So taken together, although there's been a change in the composition of the outflow through Fram Strait, the net outflow is not really very different to the previous best estimates. Okay, so now we can add all of those up and look at the total. So this is the net flux. And on this diagram, I've included a few other relatively minor sources. So one of them is the BSO, the Barents Sea opening. It turns out with this construction, with the reference salinity, that the net flux through the Barents Sea is relatively small. Fury and Hecla Straits in the Canadian Arctic Archipelago are not well observed, but we don't think they carry a very large flux. And Greenland, the Greenland Ice Sheet, of course, discharges fresh water as well. It's not particularly important in this budget, and the main reason for that is that the primary discharge from the Greenland Ice Sheet falls outside the control volume that we've constructed. It's off the east coast of Greenland and then southwest Greenland. Some of that will be included automatically in the inflow through Davis Strait in the West Greenland Current. The other thing to say is that the Greenland Ice Sheet mass loss, relative to the numbers I've been talking to you about, is relatively small. It's about 400 cubic kilometers per year. It's increased significantly, but its increase is by about 10%, so maybe it's gone up to 440 cubic kilometers per year. So compared to the uncertainty in, for example, runoff, the Greenland Ice Sheet is insignificant. However, the other thing to say about that is that it's sign definite, and it continues to increase. So the flip side to that is that you just have to ask the question, how long will one need to wait in order for the anomalous discharge from the Greenland Ice Sheet to change this freshwater budget? Anyway, the bottom line from this slide is that there has been a net freshening of maybe about 1,000 cubic kilometers per year, which is more or less outside the error bar. Compared to the decade of the 1980s and 1990s, which was more or less balanced. So we think that if you look at all of the fluxes together, there's been a net freshening consistent with the observations of increased liquid freshwater in the Arctic Ocean. So we can put that together by making a budget of liquid freshwater volume, which is V, and ice volume, which is I. And so they just change, because they're conserved quantities, they just change according to the fluxes across the edges of the control volume. So for example, for liquid fresh water, you have the inflows F in, which are the things on the left-hand side of the schematic, outflows F out, and then melting. So the M is an exchange between the reservoir of liquid fresh water and ice. And then you have a similar kind of budget for the ice. And we have each of the terms on the right-hand side from these observations. So we can integrate those and see how the V changes over time based on the observations of the way in which the sea ice volume has changed and the fluxes in and out. That's what you get, that's the red line on the diagram on the bottom, and you can see that the liquid freshwater volume, according to that analysis, has increased by about 12 or 15,000 cubic kilometers, about 1,000 cubic kilometers per year for about a decade. That's consistent with the green arrows, which are these independent estimates based from Ben Raber's work, which went out and made salinity observations in the Arctic Ocean and then integrated those. So there's consistency between these two independent methods to estimate the liquid freshwater content, which I think is useful. And it's also true that we are outside the error bars. It's pretty uncontroversial that liquid freshwater has been accumulating in the Arctic Ocean, principally in the Beaufort Jar over the last 15 years. Okay, so this is the diagram showing the before, after, and the difference. The schematic budget for the first couple of decades, the decade of the 2000s, and the difference. So the accumulation of fresh water, which is principally in liquid fresh water and principally in the Beaufort Jar, is driven mainly by increased meteoric sources, precipitation, and inflow through Bering Strait. There's less ice overall, and the outflows are more or less steady, or perhaps slightly decreased. Okay, so that was published 2 or 3 years ago. The measurements continue, and I'd like to give you an update of the current status on these various different time series. So the biomass product continues, and of course we measure sea ice extent from satellites on a regular basis. This is the best known part of the story. The decline continues, unsurprisingly. On the inflow side, we have not yet redone the analysis of the ERA interim data product, but I think that there are now better atmospheric analyses to do this with. For example, the Arctic system reanalysis would be a better source. That doesn't mean to say that it's a perfect source, because there are lots of issues associated with these reanalysis products for fresh water, which we can talk about in the questions if you're interested. There are some new observations from river discharge, so those are the blue stars extrapolated up for the whole basin. They show increasing discharge for the last few years. I do not know what the status of those river discharge observations are. There was nothing about this in the most recent and last year's NOAA report card. In the Bering Strait, the moorings are still there. They were recovered and returned around, and the freshwater inflow has continued to increase. So it is now more or less as large as it's ever been, according to Rebecca, and she is funded for the next year or two. The instruments remain in the water. So the preliminary take-home message from all of this is more of the same, increasing inflow. On the outflow side, we have new estimates for the ice flux, which is more or less unchanged. We do not yet have new estimates for the freshwater flux, although the data they exist, and Laura de Steur at the North Polar Institute is analyzing them, and the array is being redeployed. And this probably has the most stable funding of all parts of the array that I've been telling you about. In Davis Strait, we have a few more data points which don't really show much trend. You see interannual variability more than anything else. There are data which have been recovered a few weeks ago to 2017. The analysis of that is pending, but the mooring array was removed from the water. It no longer exists. That is a big problem because Davis Strait, as you can see, is one of the major drainage channels out of the Arctic into the North Atlantic. So the preliminary analysis of this update is the outflow is more or less unchanged. And so this difference plot that I showed you a moment ago, I think still applies. Steady outflow, continued inflow, and continued net convergence and increase of liquid fresh water in the Arctic. Okay, let me say a little about mechanisms and then prospects and move to downstream impacts. I want to focus on the Beaufort Gyre. So our best understanding, which is rudimentary, is that the Beaufort Gyre is a wind-driven circulation. It's driven by the Beaufort sea level pressure high, it's anticyclonic, and it is relaxed by eddies. So there's Ekman pumping at the surface, which converges the surface layer, it pumps down the halocline, it lifts up the sea surface, and it stores fresh water. And so this diagram, the colors show the liquid fresh water content, and then the streak lines show ice drift from satellite observations, and you can see the clockwise anticyclonic circulation in the Beaufort Gyre. So we think that the wind is the primary driver of the Beaufort Gyre. And with Kyle Stewart, I did some experiments a few years ago looking at the way in which the wind can control storage of fresh water in the Beaufort Gyre, the place where most of the fresh water is stored and where most of the extra fresh water is stored. And so we ran a series of experiments, you can see on the bottom right, a time series of the freshwater content. So this 6 means 60,000 cubic kilometers. So this is about 2/3 of the total freshwater content in the Arctic. It's in the western part of the Arctic, focused on the Beaufort Gyre. The black line shows a control when we hold the wind fixed. There's interannual variability. It's interesting, actually, the interannual variability is about the same size as many of the fluxes I've been telling you about. So this is unforced internal variability. And then we do some perturbation experiments. For example, we do a red one, which is applying its atmospheric forcing from the wind corresponding to winter 2007, which we call accumulate, because this is a strong Beaufort high, and so we would expect the Beaufort Gyre to spin up, we expect the halocline to be pumped down, the sea level to be raised up, liquid fresh water content increases. And you can see that happens over a period of about 15 years, and it goes up by about maybe 10,000 cubic kilometers. In these experiments, we switch the wind and we hold it fixed. And then the blue one is what we call release, and then we switch to another atmospheric state, which is characterized by summer of 99, and this is a case where the Beaufort high is particularly weak, and the jar spins down. And you see, at least initially, that there is loss of fresh water. But actually, in both these cases, both the accumulate and the release, after about 10 or 15, 20 years, you get a rebound. If you want to stimulate a large release of fresh water in this system with the wind, you have to initially prime the system by accumulating, and then switch the winds to release. And that's what the green trace shows you. So you initially have a strong Beaufort high, you accumulate the fresh water, and then you switch the wind to this release mode, spin down the Beaufort gyre, and it comes out through the Canadian Arctic archipelago, principally into the subpolar Atlantic. And of course, that is the state in which the system is currently sitting. It's preconditioned in this way. So I just want to show you a movie of what that looks like. So this is a movie. The colors show you the liquid freshwater content in meters. You're now accumulating fresh water. So what you should see in the Western Arctic is it gets redder, and the subpolar North Atlantic is white because it's drained of liquid fresh water. And then in a couple of ticks, it's now the winds have switched, and you're now releasing the fresh water. So the Beaufort gyre is spinning down. And you should see loss of liquid fresh water from the Arctic, and the Western Arctic in particular, and then infilling of blue liquid fresh water in the subpolar North Atlantic. And the drainage route is principally through the Canadian Arctic archipelago. So the wind, we think, controls a lot of this accumulation. The real Arctic is accumulating fresh water for more than one reason. This is just the wind. This is part of the story, but the real Arctic also has changed sources of fresh water, in particular runoff, precipitation, flow through Bering Strait. That's excluded from these simulations. But the point of this is that the wind can stimulate relatively large either accumulation or release of liquid fresh water. Okay, let me say I have one slide on prospects, and then I'll talk to you about the subpolar North Atlantic. Couple climate models show that these trends will continue. So on the left of the time series, you can see the red line. That's our best estimate of what the real system is doing. And then you see the sample of 4 couple climate models through the rest of the 21st century. Actually, they do quite well, I think, with respect to the total amount of liquid fresh water. At their starting point, they underestimate the rate at which liquid fresh water is being accumulated, and I think that's mainly because they underestimate the speed at which the sea ice is lost. But nevertheless, they show continued accumulation through the century. That's associated with increased meteoric sources, less ice, although the ice eventually disappears, and so the ice becomes really rather unimportant, for example, through the last 50 years. And then there's also increased export, but a net imbalance overall. A few of these models, for example, GFDL-CM3, shows a cyclic behavior where there is periodic release. None of these models get the dynamics I was just showing you a moment ago in that animation. The lower panels show, the basic message from the lower panels is that there's disagreement between climate models about the pattern of accumulation of liquid freshwater content. So these are the differences in liquid freshwater content for these 4 models. They all accumulate liquid freshwater content over the century, but the patterns are all quite different. Okay, so what's happening in the subpolar North Atlantic? Well, of course, we have many observations there. This is some results from Jan-Erik Tesdal's recent manuscripts. It's been freshening in the subpolar North Atlantic between about 2004 and 2015 at about 0.2 PSU per year, minus 0.2 PSU per year. So this is an Argo product. It's freshening across the Labrador Sea in the central North Atlantic. The 2 time series on the right show the time series of salinity in the Labrador Sea, which is the one on the top, or in the central Atlantic, which is the one beneath. The salinity has been declining. You can see, for calibration, a great salinity anomaly. So the great salinity anomaly involved a salinity anomaly of about 0.1 or 0.2. So these fluctuations are at that level. The great salinity anomaly requires about 10,000 cubic kilometers of fresh water, and it's believed to have been released from the Arctic into the Atlantic. And then the lower right shows the distribution over longitude, but I will skip ahead from that. Eric thinks that the principal driver of this freshening is changes in the gyre. So although we'll skip over the details, what you see on the right is that the gyre is accelerating, which means that the dome is lifting up and sea level is pushing down over this decade. And so the current is spinning up, and the accumulation in the Labrador Sea in particular is basically just taking ambient fresh water in the subpolar jar, for example, in the East Greenland Current, and moving it more rapidly at a faster rate into the Labrador Sea. That spin-up of the jar is associated with the wind stress curl in particular east of Greenland, and that's what the time series on the lower left shows you. Okay, so there's freshening associated with jar spin-up by the wind the year before. It's also been changing its temperature. So there's this nice paper by Peacock et al. And for the 1990s to mid-2000s, it was warming. And then since then, it's been cooling. So most recently, there's been cooling and freshening in the North Atlantic. Now, they do a nice analysis in this paper of an echo simulation, so they can look at all of the various different terms that contribute to the warming and cooling. They only look at temperature, they don't look at fresh water. In their model, which is moderately realistic, the cooling is associated with changes in the gyre circulation at nominally 45 degrees north. That's associated with changes in the wind stress curl. So again, the story is that it's changed currents in the subpolar North Atlantic associated with changed winds. Okay, I will skip that then, and I will show you this final one. So this is Labrador seawater. So the Labrador seawater is most recently colder and fresher, which is what you would expect from the surface of the subpolar North Atlantic being colder and fresher. And it's also denser. So this, although it's fresher, it's denser, meaning that the temperature is dominating the density. And I better skip up and forward and finish. Okay, so there's been freshwater accumulation in the Arctic, particularly in the Beaufort Jar. It's principally due to increased meteoric sources. The outflow is really not significantly changed. These statements are consistent with each other, and they have independent methods. We think that in order to stimulate a large freshwater release, you would need to switch the winds once the Beaufort Jar is preconditioned, which it seems to be right now. Climate models suggest this will continue. The subpolar North Atlantic has freshened and cooled despite slightly weaker outflows. And so it doesn't appear that there is necessarily a role for Arctic freshening in the change in the subpolar North Atlantic salinity right now. Instead, it seems to be more a story of wind changes and circulation changes in either the gyre or the AMOC in the North Atlantic Ocean itself, rather than changes in the export. And then the final question is a speculation about orchestration by the wind. Okay, thank you.
Thank you, Tom. Our next talk will be by Fiammetta Straneo, Ocean Forces Greenland, and Greenland Forces the Ocean, a two-way exchange in Greenland's marine margins. And let's escape here.
All right, let's see, and just by clicking?
Yeah, you can click the mouse or use that.
Okay, great, and pointer. All right, so I'm going to be talking about Greenland's changes and really their interaction with the ocean. So both the ocean as a driver and a receiver of the change. And so the Greenland Ice Sheet has been losing mass. This is a nice record that we get from the GRACE satellite. And right now it's like one measure of this decline, it's contributed over the last 15 years or so about 7.5 millimeters to global sea level rise. And one of the nice things you can see from these data is the large seasonal variability in ice loss, or the seasonal variability in accumulation and loss in Greenland, and a lot of this has to do with surface melt, and this is the big melt of 2012. So in terms of context for sea level rise, which is one of the main reasons why we care about Greenland changes, so in gray or white are the ice sheets and the glaciers outside of Greenland and Antarctica, this one, Antarctica, Greenland. And this is sea level rise contribution from thermal expansion of the ocean. And so land ice is contributing about 60% of the global sea level rise. So the sum of these three, thermal expansion is about 40%. And of the land ice, Greenland is about let's say of the total, it's about 20%, and that's roughly double that of Antarctica. And one thing to remember is these partitionings change throughout the decades, and slowly, as more of the land ice outside of Greenland and Antarctica has melted, Greenland and Antarctica's contributions to sea level rise are picking up. So that's one major impact of Greenland change. And why is Greenland changing? Well, in part because of increases in air temperature over the ice sheets, and so you get extensive melt in the summer, and you have some extreme years. I mentioned 2012. This is a reconstruction of melt extent, and it extended over the entire ice sheet. So this is something that the models are not perfect, but they're slowly doing better and better. And so we can predict some of this given changes in air temperature using regional atmospheric models. The ever change in Greenland is less easy to predict. It's due to the speed up and retreat of glaciers. So this is a dynamic change. This is an example of Helheim Glacier going into Sermelik Fjord. This is where the front was, the glaciers here, 2001, and it underwent a rapid retreat over just a few years. And so this is an example of a dynamic change. The glacier sped up, almost doubled its flow rate, it thinned considerably, and it retreated several kilometers. And the changes over these few years by this glacier alone amount to about 0.5 millimeter of global sea level rise. So the key here is quick change, and some of these glaciers can really pump out a lot of ice over a short period of time. And what's driving these changes? Well, we're not completely sure. This is an area where there's a lot of research, especially from the glacier ice sheet modeling community. But sort of both glacier and existing data suggest that the retreat and speed up of these glaciers was triggered by a change at the marine terminus. And so this is an example of a glacier in Greenland. It's grounded in maybe 600 to 1,000 meters of water. It's trapped in a fjord that usually has a floating portion, maybe sea ice, maybe an ice melange. And so the idea is if something happens and this floating portion breaks off or decreases, then the glacier can respond to this loss in buttressing in essentially nonlinear ways and again speed up. And so one of the questions that it's really important to address is how changes in the ocean, like the subpolar North Atlantic that Tom just changed, can propagate onto the continental shelf. This is one of Tom's models in the fjord and affect the ice ocean margin. And I really use this slide to show there's a variety of space scales that need to be addressed by models to cover this problem. We go from the large-scale ocean circulation, which we think, for example, the climate models can do an okay job at, to processes and variability on the continental shelf, which is not as easy to do for models that are maybe 1/4 of a degree or coarser. And then you have the fjords, which are effectively absent from most regional and definitely all ocean models and climate models. and then processes at the ice-ocean exchange that happen over tens of meters that we are only now beginning to understand. So that's a reason to look at how the ocean affects Greenland, but there's the reverse of this question, which is how Greenland's changes are affecting the ocean. And so these are just some figures from recent papers that just summarize the different ways in which people are starting to study the impact of Greenland ice loss on the ocean. And so there have been a number of studies now looking at potential impact of Greenland meltwater discharge, its increase on the overturning circulation. This is a simulation from Klaus Boning, so they forced increased freshwater discharge around Greenland, and this is an example of where the freshwater has gone after some time. And if you look at the ranges of models and answers, they vary greatly, and hence the question mark. I would argue, and I'm going to show that we're not quite in a position to study this problem yet because we don't really understand the meltwater pathways into the ocean. There's a recent nice study by Irina Overim trying to quantify the sediment discharge from the Greenland ice sheet. And so this is an example of a land terminating glacier and quantification of sediment fluxes from space. And one of their conclusions is that even though Greenland only accounts for about 1% of the fluvial fluxes around the world, it accounts for about 8% of the sediment deposition into the ocean. So that's significant. This is another example on Greenland discharge impact on marine ecosystems, where essentially they argue that the blooms, not just localized around the continental shelf, but even in the Labrador Sea, are tied to the nutrient discharge from the ice sheet. And so somewhat connected with this, as you discharge more sediments, or as you discharge sediments, then you can trigger spring blooms. And so this is an impact on the ecosystem. And so this is now the arrows in reverse. As Greenland melts, you have increased freshwater discharge. It has to come out of the fjords onto the continental shelves and potentially get into the large-scale ocean. And again, this is something that models cannot do. We don't really know how to do yet. And so we're spending a lot of time trying to understand this from an observational perspective. And so the point here really being that the fjords and this margin of glacier-ocean exchange is a really sort of small area, but very relevant, small volume contributor to the interaction of the ice sheet and the ocean. And so the glacial fjords and the outlet glaciers that flow into them are effectively the connectors of the large ice sheet with the large-scale ocean. And so they're really important, but really understudied. And of course, this is a multidisciplinary complex problem that involves a really wide range of space and time scales and processes. So I just want to summarize a little bit of what we've learned over the last decade or so in working in the fjords and at the glaciers' margins to start putting together the pieces of the puzzle of this connection. And so this is a schematic of the large-scale ocean circulation. You have warm waters from the subtropics, flowing poleward, different pathways, some going into the Arctic, Baffin Bay. You have cold Arctic freshwaters. This is Fram Strait. Tom just talked about the connection through Nares and Davis Strait. And one of the things we've seen in pretty much all of the deep fjords, which correspond to the deep glaciers in Greenland, is that some version of these warm waters from the Atlantic make it into the fjords. And so again, this is a snapshot from the same fjord in southeast Greenland in the wintertime, actually. And you can see the warm water almost 4 degrees or over 4 degrees in some areas, and then the cold Arctic water blue above it. And so this is evidence of a direct pathway connecting the large-scale ocean to the ice sheet margins. That was a snapshot. It's very important to interpret snapshots for what they are. And so one important contributor to our understanding of the glacial fjords have been moored measurements. And so they're difficult because sometimes the icebergs are where the mooring, where you'd like to deploy a mooring, and sometimes they're where a mooring comes up, and sometimes they're on top of a mooring. And so, but what these moored data have shown us is that these fjords are very dynamic. They're governed by coastal processes, which in turn are strongly influenced by atmospheric variability. And so, again, this is a 9-month record. This is velocity, and you can see the red and the blue. Red is in, blue is out. Very high frequency variability of flow in the fjord. This is a long flow and associated with large variations in temperature. And these short-term variations are associated again with synoptic weather events. These are low-pressure systems propagating poleward in the North Atlantic storm track. They generate these very strong winds and change conditions on the shelf, and the fjord responds. These are downslope events. They're a mixture of essentially low-pressure system-driven flow and katabatic wind events. They can be very strong, almost hurricane intensity, and again, they drive a dramatic response in the fjord. I mention these because these dynamics, atmosphere, ocean, are what in part governs the flushing of waters in the fjord, the recirculation of waters in the fjord, and hence the heat supply to the glacier. Looking at longer time scale, this is a record from, again, the same fjord in southeast Greenland where Helheim discharges. And there is a lot of interannual variability, a large seasonal variability in the upper layers. And this is roughly the depth of which the glacier is grounded. And so as we try to understand the response of a glacier to changes in ocean-driven melting, this is the kind of signal we're dealing with, which is at times several degrees in magnitude. And so this is the piece. Let's see if this video starts, maybe not. Yeah. So this is a time-lapse video of a big calving event in Helheim Glacier. And the point being, this is really the area that we would like to be measuring exchanges of heat, freshwater, and nutrients at, right? This is where it's all happening. And it's obviously a very challenging problem from an observational perspective and from a modeling perspective. And so a lot of the work in trying to understand the really near glacier dynamics, we have to go do it in smaller systems where we can actually access the ice margin, which is still calving and still not a place where you would like to spend some time. And so this is the use, just showing the use of autonomous platforms. We really need these technologies to get at the glacier margins. And one of the things that has emerged as we started as a community to make measurements really close to the edge of the glaciers is the big role played by the discharge of surface melt. And this is one of the mechanisms that differentiates Greenland and Antarctica. In Greenland right now, there are large volumes of surface melt, which are then discharged through a system of channels through the glacier, draining all the way to the bottom and coming out deep into the ocean. And they generate these localized, very turbulent structures. This is an example of a surface expression. So this is the glacier picture. You have fresh water coming down about 150 meters down, carrying a lot of sediment, and it shows up at the surface as this plume. This is an example of a model of one of these plumes. You can see the scales. This is roughly 100 or a couple hundred meters. This is roughly 200 meters. And these plumes are associated with increased melt, both because they supply the turbulent kinetic energy that allows for the exchange of heat between the ocean and the ice, and in some cases also because they change the properties near the ice. And so but they're very difficult to model and observe, right? Very small scales. So there's a lot of work now going into trying to parameterize these and the melt rate associated with them so that we can put this in models, including fjord models and glacier fjord models. The plumes are important not just over these scales, but they also drive circulations on larger fjord scales. So yet another spatial scale that we need to take into account instead of dynamics. So this is the glacier edge, this is this plume, and the red are measurements of velocity taken from a ship over the plume depth range, and this is a model simulation of the jet. And so, again, when you're trying to understand melting along the entire glacier face, the plume is tiny, a couple 100 meters, but this jet that is forced by this plume then changes the circulation in the fjord over kilometer scales. Again, these are things we need to parameterize if we'd like to get to melt rates. And then I want to talk a little bit about meltwater discharge. So there is increasing interest in trying to understand how a changing Greenland ice sheet and a changing Antarctic ice sheet will affect the ocean circulation. And so to do this, we need to specify meltwater forcing at the margins of whatever the ocean model configuration is. And so for Greenland, the models that are investigating the impact of freshwater on the large-scale ocean circulation, including the AMOC, don't contain the fjords nor the glaciers. And so we need to specify somehow how input from a glacier is converted into an exported freshwater flux from the fjord. And so this is just an example of the budget for this same fjord that I've been showing. We have estimates of the amount of ice going into the fjord. For this particular system, it's about 35 cubic kilometers. We now have rough estimates, and of this 35 cubic kilometers, through model estimates, it's hard to actually measure glacier melt, but we think because this is mostly a vertical face glacier, that the contribution, that the amount of melting here is quite small. And so most of this discharge ends up at icebergs that break off. This is a DM showing icebergs, and this is just a schematic. So now we have most of it in icebergs, and yet we'd like to give models the conditions of what's exported by the fjord mouth. And so are all the icebergs flowing out? And so recent estimates show that actually about half of the iceberg by mass melt in the fjord. And so again, if you're trying to force an ocean model, this is the input up here at the land ice ocean interface, but this is actually the output that you would want to put into an ocean model. And there's a lot of bending over backwards to try to get to these numbers, and this is just for one system in Greenland. And this is just a budget. So how does that meltwater actually exit? Is it all at the surface? Is it subsurface? And so these are some measurements using noble gases. So it's very difficult to track Greenland meltwater. It doesn't have a particular TS signature. And so when we go in the fjords and we measure temperature and salinity, it's an underdetermined system. We can't actually tell where the meltwater is going. But with noble gases, you can, because they have different fingerprints once you start measuring several of them. And so you can effectively, you're adding constraints. And so these are measurements from Surmalik Fjord, and what they show is the volume by fraction of surface melt. So this is melt that occurred above the ice sheet, and this is melt that occurred under in the ocean, and so melt of the glacier and mostly melting of icebergs, as I've just argued. And And a couple of things you should notice, first of all, that the meltwater is spread over a couple hundred meters, and secondly, that the fraction it's somewhere on the order of 2 to maybe 4 for both constituents. In other words, meltwater is being exported in a strongly diluted form, and a lot of it subsurface. So this is from these measurements and velocity measurements, the first time we've been able to estimate the export flux of meltwater, and about 50% of it occurs below 100 or 70 meters. So this is the kind of condition we'd like for every big glacier system in Greenland if we are to appropriately force an ocean model. So where are we? Well, we're about here, and we're looking at a big ice surface, and maybe we have some tools. And I like this picture because it sort of summarizes how challenging understanding the interaction of these systems has been. And so the bottom line is Greenland is changing rapidly in response to oceanic and atmospheric variability, but these changes are impacting the ocean beyond sea level rise. And so to understand and predict both Greenland's future changes as well as the impact on the ocean and the marine ecosystem, we really need to understand the exchanges where the ice and the ocean come in contact. And in Greenland, this is in these glacial fjords, which are really ice-choked and pose a major modeling and observational challenge. So sustained measurements and hand-in-hand with model development is really key to making progress here. And so I'm going to end with some of the activities that we've been involved in. There's GRISO is a grassroots network of scientists that has been looking at how to work collectively in prioritizing what some of the questions are for this problem. We had workshops, several reports, and now we're trying to move towards an observing system, which is really necessary to gather the data to constrain some of the models and inform some of the models that we need to study this problem. So I'm going to end here.
Thank you. Thank you, Fiamma. We've got about 15 minutes for the scheduled end. Maybe if everybody has some questions, maybe the panelists could come up and then they could have microphones. If we have some questions from the audience, we could get started. If not, maybe we just go early. Here we go. Yes. I'm sorry. Maybe you need to come up. I guess we don't have a microphone. Oh, the microphone is there. I'm sorry. And do your microphones? See if that microphone works. Oh, yeah.
Yes, my question is, from a global modeling perspective, what should be the first processes that a modeler should take into consideration for the issue that the models are not, are slower in projecting the sea ice loss and the impact and the related impact? So it's the stratosphere or the radiation per se. What are the first processes that modelers should consider in this perspective?
So basically the question is, what's the most critical process to get a handle on right now? Does anyone want to volunteer for that?
On what?
Well, the question is, if you're a global modeler and you had one process you wanted to get a handle on, first thing, high priority, what would that be? Maybe Amy could take a whack at that.
It's the balance of processes that determine the climate system, so I don't think it's possible to look at it from one as one process. It's the balance of processes that determine the climate system. So I just think it has to be looked at from a couple of perspectives.
Yeah, I vote for clouds and cloud processes because the difference there directly couples to the surface temperature and what the ice is doing, and the models are often tuned for tropical processes and aren't doing a real good job on Arctic clouds. Until that's cleaned up, we won't have a real solid prediction on sea ice.
So perhaps I can add that I think it depends on the quantity that you're interested in or the question that you're asking. But I think resolution in the ocean model is very important. And so a lot of the processes that I was talking about are not well represented in current generation climate models. But simply increasing the horizontal resolution in the ocean model would improve that significantly.
I'm going to add, if you're interested in sea level rise predictions, the fact that we still don't have coupled climate with ice sheet models in our Earth system models is, of course, a major problem. But it is all tied together because we need increased ocean resolution, for example, to even get at this problem of coupling. And so, yeah.
Any more questions? Larry, go to the microphone.
Yeah, Jim had mentioned the difficulty predicting sea ice extent year to year and connected to the difficulty predicting clouds. I wonder if some of these many parameters people were talking about have high interannual predictability.
In other words, is there any good news?
Yeah, if sea ice or clouds are really difficult, are there any easy problems here that, in terms of predictability?
Are there any things that we are successful in predicting the interannual variability for the Arctic? The answer so far is a chuckle.
Well, I mean, you know the answer on that. The question was whether the initial conditions at the beginning of summer on ice conditions was the main determiner of what would happen in the fall versus how big the summer weather contribution would be. And I think we thought the initial condition was probably the most important, but this last year was just the reverse. We had bare minimum sea ice extents going in at the end of spring, but the summer weather was like a decade ago and canceled out that effect. So we tend to have a run from year to year sometime in the weather, and we don't have a clue why that's happening because we think there's a lot of chaos in the jet stream and all that, but we do see some year-to-year carryover like the extreme air temperatures that I showed.
Well, this keen on that this last year, I kind of got skunked. I made my sea ice prediction, and I predicted a record low, and much to the surprise of many people, but that I would predict it. But and then I think your slide, and I saw slides yesterday that indicated that we had a record low in August and we had a record low in October, but we didn't have a record low in September when they do the prediction. Is that right? Did I? And you attributed that to clouds, basically. Am I right in all that?
Yeah, I can't remember exactly what was happening in each month. The record lows were mostly on the Alaska side, and for some reason the ice melt really slowed down on the Bering Sea side to almost zero loss during that month. Very unusual difference between the two sides. So, that's the part that's hard to predict.
So
yes, go ahead.
I can say a little about. There are certain elements of the climate system which operate on slow timescales, so they are more predictable. But of course, what you really want is to demonstrate skill beyond simple persistence. And there was a very interesting session before the coffee break this morning in the part of the convention center, which was in Texas. So you'd be forgiven if you weren't there. It was on Atlantic multi-decadal variability. And that involves changes in the Atlantic meridional overturning circulation, the North Atlantic oscillation, the SST patterns I was talking about as well. And on timescales of at least many years, maybe a few decades, it appears that there is some, demonstrable skill in correlations both in climate models and in sparse observations. I hesitate to say it's predictable, but that's a part of the climate system which is slow enough and seems to be interacting on long time scales that maybe it could work.
Okay.
So, my name is Bob Rich. I had a question about the impact of all of this freshening in the Arctic Ocean and in the Greenland fjords. And I wonder, have we seen changes in the biology of the areas that you guys are studying with regard to this increasing fresh water?
So this is not really my field. I think there are changes, for example, in the chlorophyll structure in the Arctic Ocean and in the timing of the blooms of phytoplankton in the Arctic Ocean this summer. But I think it's also important to point out that there really is not very good baseline data. So if you think that maybe the era of anthropogenic climate change in the Arctic began circa 1980 or 1985, which is when the ice decline started, more or less. Prior to that, there essentially is no data. So it's really a problem of observing the system in change with no sort of foundation.
I can offer a Russian perspective on that. A friend, Igor Melnikov, was a sea ice ecologist, and he accompanied everybody on the Sheba experiment in 1997. And associated with the increase in fresh water, he was really surprised that basically the sea ice ecosystem, which is a big part of the ecosystem as a whole. A lot of the biomass in the Arctic Ocean is in the sea ice. And he said that it had turned from what he was used to basically a brackish water system like he would find in the Baltic. So, of course, the Baltic's got a lot of fresh water in it, and he saw a lot of similarities to what he'd found in the Baltic before. So I think there's a big impact, at least on that end of the ecosystem.
Okay. And about the Greenland fjords, do you do any work in collaboration with biologists to see what's going on there?
Yeah, I think the answer, though, is I'm going to echo Tom. We are working with biologists, marine mammals, marine ecologists, but there is really no baseline. And so I think for any variability, people tend to rely on remote sensing, sort of derived chlorophyll concentrations, which around Greenland don't work very well because there's sea ice cover. And so I think the answer is we don't know yet. And we need to start making more in situ measurements. There have definitely been large changes in the fisheries, for example, around Greenland, but those are probably more driven with changes in the partition of Atlantic and Arctic water and species composition in response to the warming ocean.
Okay. Well, I have a question.
Oh, I have one too.
And actually, I have 4, but I only have time for one. But I guess it's mainly aimed at Jim. This notion of an ice-free Arctic, and when would we have an ice-free Arctic? I guess the question would be, if we, looking maybe at all the different model simulations you've seen, is there a case where through a combination of natural variability and climate warming trends, we get a ice-free ocean or nearly ice-free ocean, and then that affects the simulation from then on out? I mean, or do these models, if they have a big spike and you say, there's an ice-free summer, then do they kind of bounce back, or are they gone over the tipping point?
They bounce back.
Okay.
The issue on the models is, as I showed, first off, when we moved the bar from 2100 to 2060, we thought we were moving it really far, and that lasted about 2 or 3 years. The consensus on the cement models was like 2060, and that pretty well debunked that it's going to be earlier than that. Some models do show 2040 or so, but again, they're missing some key feedback in physics, and so I think you have to come from the understanding data, and we really don't have a good enough model to set what the time scale is. So we're really flying blind in our outlooks. The other piece of that is there's a fair amount of work that looks at the interannual variability and that it broadens the forecast to 10 to 20 years worth of uncertainty on when that will happen. But when they do hit, it bounces around for a few years. It doesn't just go gone and forever. But that's probably, over a 5-year record. And what it tends to be, as I mentioned, is it's really driven by the long-term temperature variability. So it'll go from intermittent to all gone when the temperature warms up another degree or two, which is enough forcing to keep it clear every year. Yeah. So it kind the temperature kind of has to overshoot to actually get the permanent ice free.
You know, in other words, you have to have persistently warm enough winters so that you can't grow back enough ice that they survive.
Right, and that persistence has to override the natural variability.
Okay, well, thank you. You've done a nice job. We give our panelists a congratulatory. Thank you very much. Oh, and I'll add